Factors affecting Christopher splitting. Dear children, myself Dr. Digna Varghese. Factors affecting Christopher splitting. Here you can see a table. The data of several important variables and trends can be identified here. Here the oxidation state of the metal ion for the complex vanadium hexachloride, and its symmetry is octahedral, and its delta value is found to be Christopher splitting value is found to be 15,400 centimeter inverse. And the same metal ion with coordination number is 4, that is VCl4, its oxidation state is 4, its symmetry is tetrahedral, and its value is 7,900 centimeter inverse. For the octahedral chromium complex, chromium fluoride complex, its oxidation state is 4 and the symmetry is octahedral, and its value is found to be 22,000 centimeter inverse. And another chromium complex with the coordination number 6, but the ligand is different here, and it is water. Its oxidation state is 3 plus, and the symmetry is octahedral, and its value delta value is 15,060 centimeter inverse. And for the same metal ion chromium, the ligand is again different. It is ethylene thymine ligand, and its oxidation state 3 plus, symmetry is octahedral, its value is 22,300 centimeter inverse. For the same metal ion, the ligand is different here, that is cyanide ion, octahedral symmetry with oxidation state is 3 plus, and its delta value is 26,600 centimeter. So there are a number of factors that affect the extent to which the metal orbitals are split up by the surrounding ligands. The representative values of the delta can be shown here for the complexes. So the factors affecting crystal field splitting are: first one is the oxidation state of the metal ion, second one is the nature of the metal ion, third one is number and geometry of the ligands, and the fourth one is nature of the ligands. You can see here from the table itself, the oxidation state of the metal ion is different. For the same metal ion, its value is different. Crystal field splitting value is different. For the different metal ions, different values. For the same metal ion with a different oxidation state, the value of is different. For the same metal ion, same oxidation state with the same ligand, but its coordination number is different, so its value is again, Christopher splitting value is again different. Here you can see the same chromium ions, different ligands, so the different Christopher splitting values. For the same metal ion with a different oxidation state, different will be its Christopher splitting. So these are the factors, that is oxidation state of the metal ion, nature of the metal ion, number and geometry of the ligands, and the nature of the ligands, that will affect the crystal field splitting values. Oxidation state of the metal ion. The magnitude of crystal field splitting increases with increase in ionic charge on the metal ion. Several complexes involving different oxidation states for a particular metal ion with the same ligands. Here you can see the ruthenium aqua complex. Here in first complex, ruthenium is in the +2 oxidation state. Its crystal field splitting in octahedral field is found at 19,800 centimeter inverse. And for same octahedral complex, but it's the ruthenium is in +3 oxidation state, the delta O value is 28,600 centimeter inverse. That means as the oxidation state increases, the delta O value also increases. In the case of cobalt hexamine complex, in the cobalt is in the +2 oxidation state, its delta O value is found to be 10,200 centimeter inverse, and cobalt 3 plus hexamine complex delta O value is 28,870 centimeter inverse. And for the iron complexes, iron 2 plus delta O 98 800 centimeter inverse, and for Fe3 plus hexacyanide complex, delta value is found to be 28,600 centimeter inverse. So the magnitude of crystal field splitting increases with increase in ionic charge on the metal ion. The second factor affecting the crystal field splitting is the nature of the metal ion. Significant differences in delta also occur for analogous complexes within a group, the trend being 3D less than 4D less than 5D. In progressing from chromium to molybdenum or cobalt to rhodium, the value of delta O increases by as much as 50%. Similarly, the values of iridium complexes are some 25% greater than that for rhodium complexes. Complexes of the second and third transition series have a much greater tendency to be low spin than do complexes of the first transition series. Here we can see the 3D transition metal cobalt, 4D transition metal rhodium, and 5D transition metal iridium. They are come under the same group, that is cobalt, rhodium, iridium. Here you can see the first crystal field splitting value for the same hexamine complex, but the metal atom is different, that is from the different transition series. Here you can see cobalt 3 plus, its delta value is 22,870 centimeter inverse, and for rhodium complex it is come under the group 4D series, that is 34,100 centimeter inverse, and iridium, that is 5D series transition metal, and its delta value is found to be higher, 41,200 centimeter inverse. So we can say that the delta value increases in the order 3D less than 4D less than 5D. In progressing from cobalt to rhodium, the delta value increases by 50%, and for the rhodium to iridium, its value is about 25% greater than rhodium. Complexes of the second and third transition series have a much greater tendency to be low spin than the complexes of the first transition series. It's a high spin complex, and these two are low spin complexes. The other factor affecting the crystal field splitting value is the number and geometry of the ligands. The crystal field splitting for a tetrahedral complex will be smaller than the octahedral complex. This approximate relationship is observed for vanadium tetrachloride complex and vanadium hexachloride complex, as well as for the tetramine cobalt 2 plus complex and hexamine cobalt 3 plus complex. Here we can see the hexamine cobalt 2 plus complex, its delta value is 10,200 centimeter inverse. And for the tetramine cobalt 2 complex, its value is about half of the first value, that is delta is 5,900 centimeter inverse. So the number and geometry, number of the ligands also affect the crystal field splitting value, and also the geometry. In this complex, it is a tetrahedral complex, and for octahedral complex, the delta value is higher, and for tetrahedral complex, delta value is lower. So geometry and the number of the ligands also influencing the value of crystal field splitting. Nature of the ligands also affecting the crystal field splitting value. The effect of different ligands on the degree of splitting of the absorption spectra of three chromium octahedral complexes. Three GD transitions are predicted for each one, that you can see here. One is here, and the one is here for the chromium hexafluoride complex. Chromium trisoxylate complex, it's about 3, 1, 2, 3 electronic transitions observed, and for tris ethylene thiamine chromium 3 complex also shows 3 transitions. There is a steady increase in the frequency of this absorption as the ligating atom changes from fluoride to oxygen, to nitrogen. In the case of chromium hexafluoride complex, fluorine is the ligating atom. It is a weak ligand and there is no such frequency changes. It's a lower frequency, and if in the case of trisoxylate chromium complex, the oxygen atom is the ligating atom to the metal chromium. The frequency increases, and for the tris-ethylenediamine chromium 3 complex, in which the nitrogen atom is attached to the metal, so the frequency again increases. So there is a steady increase in the frequency of this absorption as the ligating atom changes from fluoride, oxygen to nitrogen, corresponding to a progressive increase in the field strength. That you can see here the chromium complexes here, that is shown here. Chromium complexes CrF6 3 minus delta value is 15,060 centimeter inverse, and for chromium H2O6 3 plus, in which the oxygen atom is the ligating atom, so its value is higher, that is found to be 17,400 centimeter inverse, and for chromium NH363 plus complex, nitrogen is the ligating atom. Delta O value is again increases to 26,600 centimeter. This is the same case for cobalt complexes. The fluoride ligand attached to the metal atom, its delta O value is found to be lower, 13,100 centimeter inverse. The oxygen atom is attached to the metal in the aqua complex of cobalt. Delta value is again increasing, 20,760 centimeter inverse. The nitrogen atom is attached to the metal atom in the cobaltamine complex. Its delta value is again increases to 28,870 centimeter inverse. So the effect of the different ligands on the degree of splitting in the absorption spectra of complexes is different as the frequency increases with increasing the strength of the ligand attached to the metal atom. So nature of the ligands also affecting the crystal field splitting values. Spectrochemical series. It is possible to list the ligands in order of increasing field strength in a spectrochemical series. The spectrochemical series is a list of ligands arranged on the basis of ligand field strength and a list of metal ions based on oxidation number, group, and its identity. Here you can see the spectrochemical series of ligands. The halide ions I minus Br minus is the least field strength ligands. High field strength ligands is cyanide and carbonyl ligands. The order is like that: I minus, Br minus, S2 minus, SCN minus, Cl minus, N3 minus, F minus, urea, hydroxyl oxalate ion, O2 minus, H2O, NCS minus, pyridine, ammonia, amine ligands, ethylenediamine, bipyridine, phenyl, NO2 minus, CH3 minus, C6H phenyl, Cn minus, then CO. So these are the spectrochemical series. The ligands, it is a list of the ligands in order of increasing field strength in a spectrochemical series. So spectrochemical series is a series, an arrangement of ligands according to their ability to increase crystal field splitting for a given metal center. The weak field ligands are in the left-hand side of the series and the strong field ligands are arranged in the right-hand side of the series. They are on the top. If it is a strong field ligand, the delta O value for the octahedral complex, the delta value is increased here and then the pairing energy. Okay, but it is a weak field ligand, delta value is smaller when compared to pairing energy of the electrons. So for a D4 configuration, if it is a strong with a D4 metal ion with a strong field ligand, it undergo the electrons are arranged in this way 1, 2, 3, 4 because pairing energy is less here. So pairing takes place. But in the case of a weak field, for the same D4 metal ion, the electrons are arranged in this way D3, then 4th electron come to the higher level because pairing energy is high here. Okay, so strong field ligand forms low spin complexes, weak field ligands forms high spin complexes. The weak field ligands are those ligands that come on the left hand side of the series, that is I minus Br minus Cl minus F minus OH minus H2O. Strong field ligands are come on the right hand side of the series, that is ammonia, CO, carbonyl, Cn minus, etc. And the delta O value is small here for weak field ligand. It acts as both sigma bond donors and also pi donors. But in the case of strong field ligands, delta O is large and it acts as pi acceptors. Pi acceptors means metal ions in the high electron rich state, and the ligands donate electrons to the metal. It will undergo a destabilization in the metal ion case that will donate the extra electron to the ligand's orbitals. So the ligand accepting electrons from the metal ion. So it acts as a pi accepting ligands. So the right hand side of the series are always act as a pi acceptors. Left hand side of the series act as sigma bond donors and also pi donors. Estimating the value of delta. Jorgensen has developed a means of estimating the value of Christoffel splitting for an octahedral complex by treating it as the product of two independent factors, that is delta O is equal to F into G. Here you can see a table, that is the selected values of F and G factors. For the ligand bromide, their factor is 0.72, SCN thiocyanate ion, their factor is 0.73, and Cl minus, their factor is 0.78, and azide ion 0.83, fluoride 0.9, oxalate 0.99, water it is 1, thiocyanate or it is isothiocyanate it is for 1.02, glycinate for 1.18, pyridine 1.23, ammonia 1.25, ethylene diamine 1.28, bipyridine 1.33, cyanide 1.7. For the metal ion, the G factor is there. For manganese 2, 8, for nickel 2, 8.7, cobalt 2, 9, vanadium 2, 12, iron 3, 14, chromium 3, 17.4, cobalt 3, 18.2, ruthenium 2, 20, manganese 4, 23, molybdenum 3, 24.6, rhodium 3, 27, technetium 4, 30, iridium 3, 32, platinum 4, 36. And here you can see an example for nickel hexa aqua complex. Nickel is in the +2 oxidation state. We can calculate the delta O value for nickel octahedral complex by multiplying F into G. F for water is found to be 1. Okay, 1 into 10 raised to 3 centimeter inverse. And for G factor for nickel 2 plus is, you can see here 8.7. So 8.7 into 1 into 10 raised to 3 centimeter inverse, that is 8,700 centimeter inverse for its delta value or Christoffel splitting value. It is developed by the great scientist Jorgensen. According to Christoffel theory, the ligands change the difference in energy between the d orbitals, that is delta, that is called the ligand field splitting parameter or crystal field splitting parameter. Ligand field splitting parameter primarily reflected in differences in color of similar metal ligand complexes. Here you can see from the picture the difference in colors for the same ligand complexes but different metal. So the ligands attached to the metal that can change the energy difference between the d orbitals of the metal and reflected in different colors of similar metal ligand complexes. Here the hexa aqua complexes of iron, cobalt, nickel, copper and zinc. You can see different colors. The color is due to the fact that the ligand field splitting parameter. Some ligands do not form complexes with a particular metal ions. According to spectrochemical series, the color and electronic spectra is also related. The striking colors of the transition metal complexes are a direct result of the d orbital configurations. The colors are often characteristics of a particular metal ion's geometries and oxidation state. For example, octahedral cobalt 2 complex is generally pink. Tetrahedral cobalt 2 is generally blue. Octahedral nickel 2 generally green. Square planar nickel 2 is generally orange. High spin octahedral iron 2 complex is generally green. Low spin iron 2 is red or purple. 6 coordinate copper 2 is generally blue. Tetrahedral copper 2 is generally yellow. But high spin iron 3, high spin manganese 2, copper 1 are generally colorless or very pale due to D5 configurations and D10 configurations. Light absorbed by octahedral coordination complexes, that is, a substance absorbs photons if the energies of the photons match the energies required to excite the electrons from the lower level to the higher energy levels. That is, light energy is equal to h nu, that is corresponds to the value of delta O. So the E is the energy of the light absorbed, h is the Planck's constant here, and nu is the frequency, and delta is the crystal field splitting energy or the crystal field splitting factor. The calculation of the magnitude of delta O in such a way that delta O is equal to E light, that is energy of the light, that is equal to h nu, that we know. Lambda is equal to c by nu. Nu is equal to delta O by h. Okay. Here delta O is equal to light energy, that is equal to h nu. Lambda is equal to c by nu and nu is equal to delta O by h. Or we can write it in this way as delta O is equal to hc by lambda. That is V is equal to, lambda is equal to c by nu. So h is the Planck's constant 6.626 into 10 raised to minus 34 joule second. C is the velocity of light 2.997 into 10 raised to 8 meter per second, and into number of particles, that is 6.022 into 10 raised to 23 divided by lambda, that is corresponding to 492 into 10 raised to minus 9 meter, that is equal to 243 kilojoule per mole. That is the value of delta O. Delta O is corresponding to the energy of light, that is 243 kilojoule per mole. Thank you for your attention.